Hi, first of all, I will introduce our group members. First, we have our group leaders, Noor Hafizatul Dania. Second, we have Said Haris Al Idrus. Third, we have Muhammad Firdaus, and the fourth is Shen Si Yang. So, for the introduction, principles of chemical engineering, methanol is widely used as a fuel additive, solvent, and raw material for formaldehyde production, acts as a clean energy carrier supporting sustainable chemical manufacturing. This project focuses on designing a methanol production plant using syngas from natural gas reforming, following global trends in green industry. A process flow diagram illustrates all major units operation from feed purification to product recovery to monitor material and energy flow for better process integration. So for the introduction, chemical engineering fluid mechanics, efficient fluid transport is crucial for safe, reliable, and cost-effective plant operation. In the methanol production process, the piping system handles syngas, methanol, and processed water under different temperatures and pressures. Additive piping instrumentation diagram (PNID) includes proper pipe, pump, valve, and fitting size. Pressure drop calculation ensures smooth fluid flow with minimal energy loss considering flow regime, viscosity, density, and friction. So this is the process flow diagram for methanol production. So for the function in process flow diagrams, first we have synthesis gas, combines the fresh syngas feed like H2 or CO with the unreacted recycled gas from the synthesis loop. Second, we have methanol synthesis reactor, the core of the process. Syngas react over catalyst like cuprum to form crude liquid methanol, water and unreacted gas. Third, we have separator, cools the hot reactor effluent and uses a sudden drop which is flash to separate the mixture into crude liquid methanol. Fourth, we have purge, splits the unreacted gas stream. Most of the gas is sent to the recycle mixer, but a small portion is removed to prevent the buildup of inert gas like CH4. And the fifth, we have distillation columns, a series of two or three columns that purify the crude methanol. And the sixth is we have compressor. It raises the pressure of the combined syngas, which is fresh feed plus recycle, to the high operating pressure between 80 to 100 bar required for the methanol
So now we'll be
synthesis reaction.
calculating the mass balance calculation of reactive system. So here is all the assumption where it is in steady state operation. The confirmation basis is reacted completely. The total gas feed is 100 kilomole per hour with its composition of hydrogen, carbon dioxide, and also inert gases. And there are two primary reactions in the reactor. So this is the labeled flowchart to visualize our problem. The next step is to calculate all the molar flow rate of the input, change, and output and put it in the table. So if the input is consumed, the change will be in negative sign, while if it's generated in the product, it will be in the positive, the change will be in positive sign. So then the total molar flow rate will be 50 kilomole per hour, and then we convert this molar flow rate into mass flow rate by multiplying with the molar mass of each substance, and we'll get the total mass flow rate of 1320 kilogram per hour. This calculation demonstrates mass balance for a non-reactive distillation system. Our goal is to separate methanol and water. The key assumptions are steady state operation and a separate efficiency of 99% for methanol recovery in the top product. The input stream is 30 kilomole per hour of total feed consisting of 25 kilomole per hour of methanol and 5 kilomole per hour of water. By following the fundamental rule of input equals to total product plus bottom product, we can simply find the equation balance. So the first step is to calculate the methanol with 99% recovery, and after that we can calculate all the other molar flow rates of methanol and water in both and top bottom streams. After that, we have to convert these molar flow rates into mass flow rates using respective molar masses by multiplying it with the molar flow rate and the molar mass. This conversion will give us the final mass flow rate and mass fraction for all streams. The inlet stream is 890 kg per hour, while the top product is 794.24 kg per hour, and the bottom product is 95.76 kg per hour, which is mostly water. The final balance confirms the input is equal
The
to the
energy
output.
balance for a reactive system, which is methanol synthesis reactors, consists of 6 steps of calculation method, which is properly draw and label flowchart, and the second step is prepare inlet outlet enthalpy table, and the third step is compute heat of reaction using standard heat of formation. The fourth step is calculate reaction heat rate for the actual extent for each reaction, and compute total enthalpy change rate, and lastly calculate energy balance. The energy balance of reactive system indicates the exothermic because of the negative sign in the system, which is negative 750.7 kW, meaning that the reactor must reject 750.7 kilowatt of heat to maintain the assumed condition. For non-reactive system, which is distillation column, we the total boiler heat duty is the sum of the energy needed to heat the feed and vaporize the product, where the heat of liquid, which is methanol and water, from 25 degrees Celsius to the boiling point of 64.7 degrees Celsius, and the latent heat, which is vaporize the 99% of methanol that leave as the top product. The calculated result for the boiler duty is positive 268.7 kilowatt. Since the result is positive, it means 268.7 kilowatt of heat must be added to the system via the reboiler.
Plant fluid transport is managed by a dedicated piping network. For all lines carrying methanol, we select a stainless steel for its excellent corrosion, resistance, and compatibility, ensuring product purity and system longevity. Each methanol stream is custom designed for its specific role. For instance, stream S3 from the condenser to the separator uses a 0.2-meter diameter pipe. The final product line, stream S4, which carries pure methanol to storage, uses a larger 0.25-meter diameter pipe to minimize pressure drop and reducing pumping costs. The design also carefully accounts for valves and elbows, which contribute to friction loss. This detailed layout ensured that the methanol purification and storage operations, from the condenser and separator to the final tank, are seamlessly and efficiently integrated into a single cohesive system.
So now we'll be calculating the pressure drop calculation across each key pipeline using Darcy-Weisbach equation. This is to ensure efficient fluid transport with minimal energy loss. So first we'll have to check the flow regime state using the Reynolds number, whether if it's less than 2000 or more than 4000, to determine if it's in laminar or turbulent, so that we can choose which friction factor equation we can use to calculate it. So here are the results of the calculation. For stream 1, the flow regime is in turbulent state, so the head loss calculated is 1.084 meter. For stream 2, the flow regime is also in turbulent state, and the head loss calculated is 0.188 meter. And for stream 3, the the Reynolds number is 2000 above, and we assume it to be in turbulent state, and the Hellas calculated is 1.83 times 10 to the power of negative 5 meter. For stream 4, the flow regime calculated is in laminar, so the Hellas calculated is 1.58 times 10 to the power of negative 5 meter.
Our delivery strategy for methanol focuses on safety and energy efficiency. We design the piping to be short and straight to minimize friction, and specify a large 0.25-meter diameter pipe for the final transfer line to further reduce pressure drop. For safety, we've included check valves to prevent backflow and critical leak detection system due to methanol's flammability. The calculated pump power required is highly efficient at just 16 watts. Finally, the product is stored in a large 15 by 15 meter stainless steel tank, providing a 3-day capacity. This integrated approach guarantees safety, efficient, reliable product
So,
handling.
conclusion for principle of chemical engineering, we can conclude that mass and energy balances were performed to determine flow rates, compositions, and heat duties, ensuring stoichiometric and energy requirements were met. The resulting PFT forms a complete process model that adheres to conservation laws and support utility and equipment design. So conclusion for chemical engineering fluid mechanics, the piping layout specifies sizes and fittings with pressure drop calculations ensuring minimum frictional losses. A mechanical energy balance guides methanol transfer while pump power and tank sizing ensure efficient storage and handling. That's all from us. Thank you.